Thank you very much. It's a pleasure to be here again, although the temperatures were not exactly welcoming. And you know, wherever I go to talk, and I give lots of talks, they always tell me, oh, you should have come last week. We had great weather. And there was no exception here. The book is called Is Earth Exceptional? It's this book that you see there. This is what it looks like. And you notice that there are two names there, not just mine. So just to say who they are, this is me trying to put together a whole galaxy. And this is Jack Shostak trying to make life in his lab. So that's the thing. The book deals with two main questions, but two truly main questions. One is, how did life on Earth start? And the second is, are we alone in our Milky Way galaxy, or maybe even in the universe as a whole? These are the two questions that the book is trying to answer. Now, when I say trying to answer, I didn't say that we necessarily answered it, but what we tried to do is to give you literally cutting-edge situation on these two questions. Where are the experiments in the lab right now, and where are the astronomical searches? So you know that for many years, thousands of years, people actually had pretty clear ideas about these two questions. How was life formed? Well, you know, Michelangelo gave us the prevalent view at his time. And the Milky Way, I talked about the Milky Way, you know, in Greek mythology, the word galaxy comes from the Greek, which means milk, and we call it the Milky Way. And in Greek mythology, Zeus wanted his son Heracles to become a god. He was really immortal, so he gave it to Hera to give him milk, but she was asleep. And then she woke up, and then she tore the baby from her breasts, and that the milk spurted into the thing, and that's how the Milky Way was formed. And this story actually also made it into art by the painter Rubens and by the painter Tintoretto. This is how people thought that the Milky Way was formed. Well, we think differently today. This is the Earth. It looks almost like, this lapis lazuli minerals. It looks almost like a ball of that. And the Earth is in the solar system. And the solar system has 4 rocky planets, which are Mercury, Venus, Earth, and Mars. And then it has gas giants beyond that. Mercury, I will not even mention. It's way too hot. I mean, even much hotter than here. Venus is also pretty hot, but I will mention it because it's very similar to Earth in mass and size and so on. Mars, you know about Mars. Jupiter is a gas giant, but it has many moons, and I will mention this. It has 95 known moons. Saturn has 146 known moons. Uranus has 28 known moons. Neptune has 16 known moons. And even Pluto, which is no longer considered a planet, it was demoted to being a dwarf planet, even it has 5 moons. So those moons are important, as you will see. Now, when I tell you that I'm talking about origin of life on Earth and whether Earth is something special, you have to realize what Earth looks like from a distance. And Earth looks like from a distance, I'm not sure if you can even see it. Do you see this pale blue dot here in the middle? This is what Earth looks like from about 4 billion miles. So it really looks like nothing, but here we are trying to tell whether it is something very, very special. You know, the title is Earth Exceptional, and I will talk about that. So, I'm talking about origin of life on Earth. What does life really consist of? So, there are 4 things that must happen because they happen in all life forms that we are aware of. And they are metabolism, which means the ability to harvest energy from the surrounding and use it. Genetics, which means you must have an information system which both can give instructions and also can be passed from one generation to the next. Compartmentalization, which means you need cells. All life that we know is composed of cells, biological cells. And catalysis, which means there must be something that allows for chemical reactions to happen and especially encourages them to happen faster and more efficiently. So life somehow seamlessly manages to combine these 4 things into one thing, and that's what all life on Earth does. Now, there is a problem with life on Earth as we see it today. And that problem is that everything in life on Earth today depends on everything else in a circular way. Which means, for example, you want to make DNA, let's say, which is, you know, the source of the genetic system and all that. You need to have enzymes, which are proteins, to make those. But to make the proteins, you need instructions that come from the DNA. So everything is related in a circular way like this, a bit like this drawing by Escher, where, you know, one hand grows the other and this one grows that one. And because of this circular dependence in all life as we see it today, for many years, this was considered an obstacle that cannot be overcome. Because, you know, it's of course, famous chicken and egg problem, right? I mean, what came first, the chicken or the egg? Well, you know, if one does the other, one does the other, what do you do? How can you solve this at all? So this was a very serious problem, which was considered insoluble. Now then something happened at the beginning of the 1980s. At the beginning of the 1980s, 2 scientists independently discovered something amazing. They discovered that RNA, you know, there is RNA and DNA in our life. RNA can actually also act as an enzyme, like a protein. So they found something that can both store information and instructions and can act like an enzyme, like a protein. In other words, it can act as the chicken and the egg, RNA. And these were called ribozymes. And this was absolutely amazing because that suggested a way out of that conundrum. And the way out was basically what has become known as the RNA world. Namely, the idea that life on Earth started with RNA. Because RNA could both do the instructions of things and play the role of protein enzymes. Now, just to remind you, because some of you don't remember chemistry or biology, one learns in, I don't know, 3rd grade? I have no idea when one learns that. What is RNA made of? RNA is made of sugars, phosphates, and 4 bases, which contain nitrogen in them. Sugars, phosphates, and 4 bases. The bases are, for short, I will call them C, G, A, and U. Okay? C, G, A, and U. And the phosphates and the sugars, they form the backbone of the RNA molecule. So there is a backbone, which is sugars and phosphates. And then there are these 4 bases. And the information is actually in the order of these 4 bases, how they are arranged. This C, G, A, and U. Okay? Just again to show the differences, DNA is, RNA is single-stranded. It just has 1 strand. DNA has 2 strands. It's called the double helix. So it has 2 strands, and it is made, again, of the backbone is still sugars and phosphates. The bases, I mean, 3 are the same way, but instead of U, it has 1 that I call for short T. Okay? So also 4 bases, but one of them is a different base. But look, I just told you, I don't need DNA. Life on Earth probably started without DNA. It started just with RNA, doing both the role of storing information and giving instructions, and the role of catalyzing the chemical reactions. Now, my first slides, by the way, contain a little bit of biochemistry, but I'm making this very simple. So, I mean, please don't say to yourself, but I don't know any biochemistry. You don't need to know any biochemistry. Look, biochemistry, there is nothing complicated in it. The only thing that's complicated in biochemistry, other than, of course, doing it experimentally, is the horrible names. The names of compounds and of processes. But don't be frightened by that, because, okay, so who cares about the names? Just when we describe it, for example, in the book, read about what were the problems, what obstacles were the scientists trying to overcome, and not, who cares if it was this, that, or that, or not. Now, there is something, I mentioned this because this is kind of amusing. It turns out that to start life on Earth, you needed, initially at least, 3 things: cyanide, formaldehyde, and hydrogen sulfide. Now, this is very strange because cyanide is considered today to be a very strong poison. So is formaldehyde. Hydrogen sulfide is not a poison, but it's the thing that, the smell of rotted eggs. That's that. So life on Earth almost certainly started with some very strong poisons and something with a very bad smell. This is how life on Earth must have started. These are these guys. Now, why cyanide, by the way? Again, easy to understand. These bases that I talked about, U, A, C, G, yes? These bases, they contain carbon and nitrogen. So it is good to start with something that already has carbon and nitrogen in it. And cyanide is hydrogen, carbon, and nitrogen. So this is why cyanide plays such a big role. And cyanide and various derivatives of cyanide. There is something called cyanamide, and there is something like that. But basically, it's cyanide. So, for example, how did this cyanide, how was it there on Earth to start with? Well, in the Earth's atmosphere, in the early Earth's atmosphere, there was lots of cyanide in the atmosphere. And it rained down with the rain onto the surface. Then on the surface, there was iron that came from the crust of the Earth itself. And that formed something that's called ferrocyanide. Iron together with the cyanide. And the good news about this ferrocyanide, that it can accumulate as layers. So at the bottom of these lakes, layers of ferrocyanide formed. Now, of course, you still needed to somehow separate the iron from the cyanide because you really needed only the cyanide to actually get it going. And that turned out not to be a problem because the early Earth was also, there was lots of volcanism and asteroids hitting. So there are all kinds of heat sources, lava flows, things like that, which we know once they went over this layer of ferrocyanide salt, it separated the cyanide and made it available for what you need. I hope nothing happened there. Maybe some accumulation of cyanide? No. So that was that. Now, I have here 2 or 3 slides which have these chemical structures on them. Very simple. Please don't be afraid of this. All I want here is to mention this concept which I call systems chemistry. Systems chemistry is a genius idea. Because you see, originally, all the biochemists that worked on origin of life, they said, oh, I need sugars, phosphates, and this base. Okay, let me first try to combine the sugar with the base, and then add phosphate to it. And this is how RNA was made. And this is what is delineated in the top row there. It turned out that it was impossible. They just, whatever they did, they couldn't make the sugar connect to that base. Didn't work. What did work? It turned out that you can make some intermediate compounds, and those intermediate compounds could then give atoms to sugar, give atoms to this, and make the two. So in this case, there was something which has the complicated name 2-aminoxazole, but it doesn't matter. 2AO for you, 2AO. 2AO is an intermediate. Pax. It creates both that and the other thing. And another such intermediate called RAO, named even more complicated. Ribosaminoxazole, never mind. But here is something fantastic about this RAO. This RAO can crystallize, and as it crystallizes, it gets out of the solution and again can accumulate. So you accumulate these intermediate stuff, and from there you make the next step in the thing. Amazing, amazing. This is just unbelievable. Bottom line of all this, don't look at this at all. Bottom line, I'll tell you what the bottom line is. The bottom line is that biochemists have now shown in the laboratory that under conditions that are completely compatible with the conditions on the early Earth, they can make 2 of those nucleobases that I mentioned, C and U. I told you that there are 4 nucleobases of RNA. 2 of them, we know how they were probably made on the early Earth. There are 2, A and G, which we still don't know. But people are working on this, and as we speak, okay? But 2, they know how to, not only that they know how to make, you see, they can do all kinds of chemistry and make them. The question is is it a plausible path that could happen naturally on the early Earth? And they showed that yes, under conditions that were on the early Earth, these 2 nucleobases were happening. Not only that, that same chemistry also can produce the sugars. The phosphates were easy, they are there all the time. So I told you that RNA is made of nucleobases, sugars, and phosphates. Phosphates are easy, sugars could be made, 2 of the 4 nucleobases could be made. We almost have the RNA that we think started life on Earth. More than that. Some of you may have heard that proteins, I mean, because you know there are these nucleobases, and then there is proteins. That's the other part of life. Proteins are made of building blocks, which are called amino acids. There are 20 amino acids that make all life on Earth. Every form of life on Earth uses 20 amino acids. There can be more amino acids, but all life uses only 20. Precisely the same chemistry that I described here, biochemists have shown, can make 12 out of the 20 amino acids. So the same chemistry of the early Earth can make 12 of the 20 amino acids that do life. This is where we are in terms of the beginning of life on Earth. We don't know yet how to make everything, but we know how to make quite a bit under conditions that are extremely plausible. Okay? Good. That's good. This I mentioned just in passing. Some of you may have heard that the molecules of life have a handedness. I mean, amino acids, for example, they could come in a form that is like our left hand and in the form that is like our right hand. In principle, life could be made of any of those. It doesn't matter. But all life on Earth uses left-handed amino acids. Now, whether it's left or right, that is probably an accident. The question is, how come it's not some kind of a mixture? It's just, from where do we have this, we call this homochirality, that there's only one type, and so on. Many, many years, we had no idea why this happens. In the last 3 years, scientists found why that may have happened. And the reason it may have happened is that they discovered that on some minerals called magnetites, if the RAO, you remember that intermediate, forms on this magnetite, because of the Earth's magnetic field, you form preferentially one chirality and not the other. So you can get the handedness. Some people only came for the food, I guess. Now, the other thing I mentioned to you is cells. Sorry, I didn't mean to offend you. Life is made of cells. And cells are important. Why are they important? Well, first of all, cells hold the whole thing together. If you look at me and at this young lady here and so on, we have our own individuality. We're not both diffused into the environment. Right? So you need the cells. But there is something even more important. You all have heard of Darwinian evolution. Darwinian evolution means that some things give an advantage and those get, more prevalent. Now, if you don't have cells, if they not happen inside, suppose you made an enzyme that works better. Well, if it can go anywhere, you didn't gain anything. If it all happens inside the cell, then okay, those work there and they can do better and better and better, right? So we need cells. Now, to have cells, we need a membrane that surrounds the cell. The early cells were not like today's cells. The early cells were probably something very simple. They had a simple membrane, and inside they probably had this tiny piece of RNA which started doing its thing. That was how the early cells must have looked like. What's the membrane? The membrane is, some fatty acids, some lipids. Okay, the biochemists know how to make membranes. Not only they know how to make membranes, they even know how to make those vesicles to grow and to divide. What they don't know how to do, I'm telling you the things which are open questions. They don't know the membranes that they develop are very simple fatty acids, and they're not like the very complex membranes of cells today, which can do lots of things. they control all the transport in and out of the cell and things like that and so on. That they don't know how to do. But the very simple lipids, they know how to do. So we are kind of on the road there, but phospholipids, they don't know yet how to do. There is one other thing that I need to tell you about the cells. In modern cells, I mean in today's life, all the things that the cell does are controlled by machinery inside the cell. That controls what comes in, what comes out. How does this grow? How does that do? That was not the situation with the early cells, because the early cells still did not have that machinery. So everything was actually controlled by the environment. Namely, what happened outside, did the wind blow over these cells and cause them to divide or what, and so on. The things were controlled by the environment. Just to mention that life on Earth started, the earliest life forms that we find on Earth are from about 3.5 to 3.7 billion years ago. Just for reference, the Earth itself is about 4.6 billion years old. So life on Earth started relatively early in that, the very early Earth was extremely hot, so nothing could have started there. But a few hundred million years after the formation of the Earth, life already appeared on Earth. And the earliest life forms are these in the form of these stromatolites, and this is how they look today. These are basically mats of microbial life that, you find these fossils dating back to 3.5 to 3.7 billion years ago. There is one myth that I want to dispel. Now, I want to say something. This is very important to me. Everything I tell you, it is not that, first of all, we know without any doubt that that's how things happened on Earth. We weren't here 4.6 billion years ago, so we cannot say exactly what happened there. All we can say is that we find plausible paths which, under the condition that we know existed on the early Earth, could do these things. So almost every sentence I tell you, there is some biochemist who disagrees. Now I'm going to tell you something which I'm sure you read in newspapers, in magazines, if you ever were interested in the origin of life question, and that is, where did life originate? So the story you read in magazines and this, it originated in hydrothermal vents at the bottom of the ocean. This is what you read in most places. And there are some biochemists who believe that. We actually strongly argue against that. And the reason I would say we are convinced it's not that. But as I said, not everybody agrees with us. Why are we convinced? First of all, nobody has ever shown a real path for life starting at hydrothermal vents. This is an idea. And from what the idea comes, that these hydrothermal vents are now populated by lots of life forms. But the fact that there is a colonialization of hydrothermal vents now, it doesn't mean that life started there. And so that's the first thing. Second, all the experiments that succeeded in producing building blocks of life required high concentrations of the key molecules that I talked about. You cannot get high concentrations at the bottom of the ocean. It all gets diluted. Also, some of the processes, I don't know if you noticed that when I added what is needed there, I said UV radiation, which came from the sun. Well, that UV radiation does not penetrate to the bottom of the ocean. And not only that, the experiments show that you need varying conditions. Namely, you need things like evaporation, like wet-dry cycles. You need freeze-thaw cycles, things like that, all of which don't happen at the bottom of the ocean. So where do we think life started? In small lakes and ponds. In particular, alkaline lakes are called soda lakes. This is where we think it started. So, and this is actually interesting because Darwin, when he tried to speculate where life might have started, he wrote, perhaps in a warm little pond. So Darwin was apparently right, at least according to our opinion. I want now to move for the search for life outside of Earth. And astronomers here adopt a three-pronged attack. One is they look for life in other places in the solar system. That's in a way the easiest. Second, they try to look for life in planets revolving around other stars, and I'll talk about that. And then there is also a group of scientists that try to take a shortcut through all that and say, well, maybe there are some intelligent civilizations out there, and I'm going to try to communicate directly with them. Okay. So the place that has gotten most attention so far in the solar system is Mars. And Mars, when I grew up as a child, being convinced, that's what I was told, that there is civilizations on Mars. I was just in New York last week, and I saw this poster, from an old movie. This is written in French. It's Superman against the invasion of the Martians. I mean, we were convinced that there is life on Mars. Well, we now discovered that Mars is a rather arid desert. That's what Mars looks like. It's almost like what you see outside here. But, you see, Mars is a smaller planet than Earth. Because it's a smaller planet, it actually loses its heat much more rapidly, and also couldn't hold to its atmosphere. So it has hardly any atmosphere at all. So today, there is no life on Mars. But it doesn't mean that 4 billion years ago, when Earth and Mars formed, then they formed from roughly the same type of material. And so there is really no reason that not to have had some early life on Mars. This is why we keep landing things. This is the Perseverance rover taking a selfie of itself on Mars. And we know that there was liquid water on the surface of Mars. By the way, liquid water, we think, is an absolute must. If somebody asks me later, I can address if there could be other solvent other than liquid water. But we think liquid water is a must. But look here, look at this part of Mars, and look here at a different time. It looks like something flowed there. There are places where you see almost, that there were rivers and things and so on. So there definitely was life on Mars. And the InSight lander actually discovered that some 6 to 10 miles down, there is liquid water underneath the surface on Mars. So the hope is that, we will continue to explore Mars, and the hope is that we will find perhaps some signs of past life, and by that I mean not a crocodile, I mean microbial life on Mars. Okay. The question is, have we ever found any kind of life on Mars? And the answer is that there were at least 2 famous events where people thought that they found life on Mars. First, there were the 2 Viking landers that landed on Mars. They had a famous experiment where they took some Martian soil, added to it some nutrients, and thought they saw some metabolism happening. But a second experiment that tried to find organics in that found nothing. So I will say the following. 99% of the astronomical community thinks that Viking did not find anything. But there is about 1% that continue to argue that yes, Viking found something, or that even that by adding water to that soil, the experiment killed the life that was there on Mars. A second thing is this famous meteorite. It's called ALH 84001. It's a meteorite that was found in Antarctica, and it's a meteorite that came from Mars. We know that for a fact, based on the gases that are trapped inside the thing. It's for sure that, in fact, there are maybe 300 meteorites that arrive from Mars. You see, what happened is when an asteroid hits Mars, some ejecta goes into space, and some of that makes its way to Earth, and this particular one made its way to Antarctica. There was a claim that made it into even a presidential announcement. Bill Clinton announced that we found life on Mars. That turned out to be not true. They found, no, I mean, he was just, claiming what the scientists told him, and that actually, I think, was refereed by 7 people. Look, they found some forms of fossils that resembled life very much, but apparently were not life, because later ways were found how regular chemistry could actually do that without it being life at all. So that's that. So we never, so far, at least not convincingly, found life of Mars. Venus is hot. On the surface of Venus, lead melts. So it's hot. But about 2 years ago, there was a claim that high up in the atmosphere of Venus, they found phosphine, which is a phosphorus attached to 3 hydrogens. And on Earth, phosphine is made by some bacteria. So now, since then, there have been claims that they did find this, they did not find it. Some people say, okay, they found it, but it's not necessarily by life, and so on. The bottom line is that we don't really know the answer to this, but there are a few missions that are going to go to, they are called Morning Star missions, they are going to go to Venus, and we will hopefully know the answer. If there is phosphine there, what is its source, and so on. Jupiter, I told you that this is a gas giant. Nobody thinks that there is life on Jupiter. Jupiter, by the way, is turbulent all the time. Look, this is how it looks from the Juno spacecraft. This looks like a abstract painting. It is amazing. But not Jupiter itself, but its moons. And one of its moons is Europa. This is its moon, Europa, to which, by the way, in just a matter of days, the Europa Clipper is going to be launched to Europa, just in a few days, literally. And Europa, previous missions have discovered that underneath the icy surface, which is, miles in depth, there is an ocean of liquid water. Now, I told you that we don't believe that life started in an ocean, but an ocean can sustain life if it's already there. So, for example, the same asteroid hits of Mars that, threw rocks to Earth could actually throw a rock to Jupiter, to Europa even. And if that early rock happened to contain some life, that life could perhaps be sustained in the ocean underneath Europa's surface. So there is Europa Clipper, it will get there, we will find all kinds of things. Saturn, another gas giant, in itself does not have any life, but it has a few moons that are very interesting. One is Enceladus, again has a large liquid water ocean underneath the surface. Again, miles underneath the surface, but lots of water. And it has another moon Oh, and Enceladus, by the way, we see that there are cracks in the ice because we see plumes coming up, which means that we will not even have to dig through the ice. Rather, we can send a spacecraft that can fly through the plume and collect material, and we'll know what's there. It has another moon, Titan, which is really amazing. Titan could, in principle, host even two forms of life. One, it has a liquid water ocean underneath its surface. Two, it has. By the way, the reason they have these liquid oceans is because the tidal forces from Saturn, they cause the moon to flex like this, and all the friction there does heat, which generates that water. So that's one possibility, but also Titan has on its surface lakes that look like this. Look, this is like a picture of Earth taken from above, only that those lakes are not of water on the surface, they are of liquid methane, which is in forbidding temperature. Now, if there can be life in something like this, then, maybe in these lakes, life as we don't know it. Maybe life as we know it in the ocean, underneath, maybe life as we don't know it here. Now, if you're asking me, am I holding my breath to find life in these oceans? No, because the temperatures there are so low that I don't see how much interesting chemistry could have happened there. But it's still amazing, and actually we are in a situation where the Europeans had a probe, the Huygens probe, which actually went down to the surface of Titan and took pictures as it was coming down, which is absolutely amazing. There was also a plan at one point to land something like a boat on one of the lakes on the surface of Titan. By the way, if we do that, we can call it the Titanic. But that plan actually is no longer there. Okay, so far I told you about the solar system. I told you that the second prong is looking around other stars. We know that there are many places in the galaxy where new stars are born. Just look at this, clouds of gas and dust, which form beautiful pictures where new stars are being born. These are pictures from the James Webb Space Telescope. Amazing, amazing pictures. New stars are being born inside these clouds of gas and dust. And not only new stars are being born, but we know already from Hubble that around many of these young stars, if not all of them, there are disks of gas and dust, which are exactly the type of disks from which our solar system formed. So we knew already, even before we started really discovering lots of planets, that the raw materials for building planets around stars are there. And indeed, we found, to date, there is more than 5,000 extrasolar planets found. This in itself is amazing. Until 1995, we did not know of a single planet around a sun-like star other than the sun. In 92, we discovered planets around pulsars, which are these very dense objects. Nobody thought about life there. But from 95, until 95, not a single planet around a star, sun-like star. Now, thousands and thousands of them. In fact, if you sort of multiply to the whole galaxy, and I'm just talking about our galaxy, there could be as many as perhaps 1 billion planets, Earth-sized roughly planets. There are all kinds of other planets. There are water worlds, this, that, blah, blah, but we are interested really in the ones, like silicate planets. How can we tell what they are composed of? We can tell because if we can determine the mass and we can determine the radius, we can determine the average density of the planet, and then we know what it's roughly made of. So we found many, many Earth-like planets, and we do something that is, honestly, it's like magic. Look, if you have a planet that is orbiting its star, and we happen to be, our line of sight is in the plane where this planet moves around its star. When the planet goes in front of its star, as seen from by us, the light of the star, some of it passes through the atmosphere of the planet. And by taking a spectrum of that light, we can tell things about the composition of the atmosphere of that planet. And that has now been done for a number of planets. The composition of the atmosphere of planets around other stars. So, you know, there are some systems that at least originally looked extremely promising. Here is the solar system, and there is a system called TRAPPIST-1. It has 7 planets. 3 of those planets are in what we call the habitable zone of their star. What is the habitable zone? Habitable zone, you see, if you're too close to the star, it's too hot. If you're too far from the star, it's too cold. We want to be at a distance such that liquid water can exist on the surface. That range of distances where this happens is called the habitable zone. In our own solar system, the Earth is, of course, in the habitable zone, and Mars and Venus marginally so, okay? But in this, 3 planets are in the habitable zone. So we thought, aha, if we can use the James Webb Space Telescope to characterize the atmosphere of this planet, we can perhaps try to tell whether there is a possibility for life there. In other words, what we really want is an atmosphere that's out of thermochemical equilibrium. What does this mean? For example, you know that you cannot have oxygen and methane in large quantities at the same place. It's like having a room where graduate students and lots of pizza and nobody is touching the pizza. It's not in equilibrium, yes? So oxygen and methane, they destroy each other. So if you find an atmosphere that is out of thermochemical equilibrium, you know that on Earth it's out of thermochemical equilibrium. Why? Because there is life. Life does things to take it out of thermochemical equilibrium. So let me tell you what, however, happened. You see, this system, the TRAPPIST-1, the star is much smaller than the sun. So it's much less hot and much less luminous, and so everything is much closer than in the solar system. As a result, there are problems, because stars that are small like this, they have flares which can destroy the atmospheres, and there are other problems related with the fact that the stars are what we call tidally locked, which is, you know, like our moon and the Earth, which shows us all the time the same face, because they rotate around their axis exactly at the same rate as they move around. So they all the time show us the same face, you see. So that's how it happens there. The bottom line is that for those 3 planets in the habitable zone, we found that actually they have no atmosphere. They must have lost it either because of flares or because of this motion very fast. It generates currents in the atmosphere which hit the atmosphere and they can lose it. But, and here are those planets, 1E, 1F, 1G are in the habitable zone of TRAPPIST-1. So they turned out not to be so great at the end, but never mind, we tried. This is another interesting planet. It has the very interesting name K218b. When, again, they tried to determine the composition of the atmosphere, there was a claim that it has, which is this one point here, dimethyl sulfide. Dimethyl sulfide on Earth is made by plankton in the seas. So this was very exciting because it could say, oh, maybe there is some life on this. Well, it's just at one point, and actually since it has been shown that there is no way that you could really believe that one point above a background of carbon dioxide and methane. So probably not. But the point I'm trying to make, we are getting to the point where people are making claims that they see signs of life in these places. Now, what about other galaxies? There are lots of other galaxies. Some of them are gorgeous. Look at this. I mean, incredible. Just look at this. This is unbelievable. Some are interacting and doing these kinds of shapes. Look here, 4 galaxies interacting, you know. And then there is the Hubble Ultra Deep Field. This is a deep image of the universe. Every point of light here, with the exception of, you know, this one and maybe one other that has spikes here. Every point of light, I mean, this point of light is a galaxy with 100 billion stars like the sun. Okay? And this is, do you know at what area of the sky Hubble looked to make this thing? If you take a drinking straw and look at the sky, that's the area at which it looked. So you can make an estimate how many galaxies are there in the observable universe. Estimates go all the way to about 2 trillion. 2 trillion galaxies in the observable universe, okay? So you think, there must be life somewhere out there, right? I mean, this is from the James Webb Space Telescope. Well, I want to say something. It sounds like there must be life in all of these things. I mean, you know, there could be 1 in 20 zeros planets out there. So surely in one of those, there must be life or even civilization. Well, there was an astronomer, his name was Frank Drake, and he tried to write some sort of a probabilistic argument as to find how many civilizations there might be in the Milky Way galaxy. The problem with this, it's called the Drake equation. It's really not really an equation. The problem with this equation is that there are 2 things here that are determined from astronomy. And those are known now. We know what fraction of the stars have planets and so on. But then there are all these factors here which come from biology. What is the probability for life to start on a planet? What is the probability for if life started to evolve to intelligence and so on? All of those we know nothing about. And I mean nothing. So, you know, you could tell me there are 10 to the 20 such planets, surely there is life on one of them. I say not surely. Because how do I know that the probability for life to evolve on a planet, even if the conditions are right, is bigger than 1 in 10 to the 20? Maybe it's not. We don't know that. So on one hand, I want to say, how can we be so arrogant to say that in all this vast universe, we are the only ones there? On the other, I want to say, if you tell me, oh, there must be this. No, there mustn't be. Maybe there is, but we cannot tell. At the moment, we cannot tell. I told you already that some people try to find intelligent life right away. And there is an interesting point here, which is that, you know, some AI experts and computer people like, you know, Ray Kurzweil, people like that, claim that within a few decades even, intelligent machines will take over, that they will become the dominant species. Now, let's say that they are wrong and it will not be a few decades. Let's suppose it will be 1,000,000 years. That's still nothing compared to evolution. Now, if that's true, then biological life as we know it may actually be only a brief phase in evolution of complex creatures. And if that is true, then if there are intelligent species in the universe, they are probably dominated by these machines and not by things like us. And that means that even the way we're looking now for life elsewhere may be totally wrong. Because we are looking on the surface of planets, habitable zone, I don't know. All of that is meaningless to a machine. They don't even need to stay on the surface of a planet. It's actually easier for them to be in space where there is no gravity, and it's easier to build large structures and so on. Now, there are people who try to find artifacts of intelligent life on Earth. There has been even a claim that some spherules that were found that came from some meteorite that came down actually came from some spaceship because of the composition of these spherules. Now, other than that particular team, nobody believes that, but it is still, you know, it is interesting to look for artifacts because, you see, if there are very clever species out there, we may never be able to decipher their signals. On the other hand, artifacts, you know, are easier to understand. So it's a good idea to look for artifacts, but, you know, we don't know what. Intelligent, very intelligent machines may build structures that collect all the, or most of the energy of their star, you know, to be used. Or maybe even the energy of many stars to be used. Who knows? Is the solar system in any way that we perceive it special? Well, you know, there is an astronomer here at this university. She's actually in the audience here. That she and I did some work where, you know, there are some people who claim that asteroid hits on Earth were important for life to start. But you know, to have an asteroid that hit the planet, you need two things. You need to have a special architecture of the giant planets, Jupiter and Saturn. And you know, maybe systems that don't have that part, and so maybe life doesn't start there. But it's not a convincing argument. We just pointed this out. In other words, I cannot tell you at this point whether life on Earth was inevitable, given the chemistry, or really an accidental chemistry freak. We cannot tell. I want to say, though, one thing before I finish. There's one thing that we all should understand, and that is the following. You see, stars are born, and then they die. They die either by large explosions, we call supernovae, like this thing here, or by processes we call planetary nebulae, where they eject more gently their outer layers. All the elements needed for life are formed inside stars. At the Big Bang, there was only hydrogen and helium and trace amounts of other things. Everything else was formed inside stars. The carbon we need, the oxygen, all of that inside stars. Not only that, see, this atom in my body may have been formed by a star over there, and this atom in my body by a star over there. So not only are we in the universe is inside us. And that's a very powerful point, you know, to understand when we talk about life. So here, stars are born here, and they die here, or here, or here. By the way, the Pearl Jam, the rock group, chose this image for their cover of their album. So yeah, or sometimes it's explosion. So just to quickly summarize, we can make 2 out of the 4 nucleobases, and the sugars, and the phosphate, and 12 out of the 20 amino acids. We know how to make membranes. Again, all compatible with conditions that were on the early Earth. We are starting to characterize atmospheres of extrasolar planets, of which there are many, and this will happen even more. There will be a Habitable Worlds telescope to be launched roughly 2040 or thereabouts, which will characterize the atmospheres of the order of 25 extrasolar, good candidate extrasolar planets. So it will be amazing for, all of this. I may not live, unfortunately, to see it, but it will be incredible. My prediction is, it's difficult to make predictions, especially about the future. Oscar Wilde said that. My prediction is that within 10 to 20 years, we will either discover life on some extrasolar planet, and by that I mean simple life, not intelligent life, or we will at least be able to put some constraints, statistical constraints, on how rare life is. Namely, if we manage to study 100 planets and we found nothing, we say, okay, it's less than 1%, even when the conditions are right. Okay? So that's what I think. So, we are trying to answer questions which, Leonardo, the great Leonardo, talked about the microcosm and the macrocosm. We try to answer those. In my opinion, my very humble opinion, 3 of the biggest questions that exist in science today are ones of origins. The origin of the universe, the origin of life, and the origin of consciousness. We have made enormous progress in understanding the origin of the universe. I just described to you that we are making enormous progress in understanding the origin of life. Origin of consciousness, we still have some way to go. So I'll stop here, and I will take some questions, and later I'll be happy to sign books if people want them. Thank you. Can you put the lights up? Yes.
So you talked about the things that we can do and we figured out how to do, yet the things that we can't do, nobody's figured out yet we're here. So can you speak a little bit into the theory of panspermia, that
Yeah.
will be the missing link?
Well, okay, so panspermia is the idea that life on Earth was actually brought from somewhere else. But you see, panspermia doesn't solve anything, because it leaves you with a question of how did life start there? Okay, so instead of how did life start here, I'm interested in how life started there. So panspermia was never really solving anything.
Conditions could have been different somewhere.
Yes, that's right. But still you needed to then specify some chemistry from which everything went. There is a young student over there that has a question. Do I consider something like the strong anthropic principle? Yes?
By the strong anthropic principle that we should find ourselves in a universe that is life-giving, where we see no evidence of life in any nearby planets?
Yeah, thank you. So there is a weak and strong anthropic principle. The weak anthropic principle says that, there are ideas, for example, now that maybe even our entire universe is actually only one of very many universes, a multiverse, a huge ensemble of universes. In these many ensembles of universes, there could be different physics, different values of the constants of nature and so on. Of course, the weak anthropic principle says, of course we have to find ourselves in a universe that allowed us to appear. That's the weak principle. Yes, that's sort of trivial, because clearly we have to be in such a universe and so on, and it doesn't teach us much. The strong anthropic principle is really more like a religion. It says that we live in a universe that life had to appear in our universe. Not that we find ourselves in a universe from a multiverse, but that in our universe, life had to appear. This doesn't advance us at all, because it is really the same way as saying God created life. Yes. But I'm very impressed that a boy your age knows about the strong anthropic principle.
Can you conceive of a non-carbon-based life?
Yes.
And if so, what chemical basis would you conceive it
Yeah.
to be most?
Yeah. So we have a whole chapter on life as we don't know it. And it's, and it's not just non-carbon based. I mean, that's not the only thing that you could change. There are all kinds of things you could change. You could change DNA and RNA to something else. You could make life try to make life not carbon based. For example, in that case, silicon is one that has been tried a lot. You can try to do life that does not have cells. You can try to make different type of membranes of cells. You know, life with no chirality and all. All of those are being done, experiments. It turns out, amazingly, that, for example, silicon, as close as it is to carbon, it doesn't even come close to the richness of chemistry that it allows. So I'm not saying it's impossible, but I'm saying it's hard. To cite the people who did the most extensive study of that, they concluded, their last statement was, we conclude that silicon is the physics of rocks. Carbon is the physics of life. So yes, and plus, I talked about intelligent machines. That's also life as we don't know it, of course, and we discussed that as well. Yes?
In your opinion, do you think that we will create life in the laboratory in the near
Yes,
future?
yes. Yes, I believe so, yes. Look, Jack Szostak, who wrote with me the book, he's a Nobel laureate. I've known him for more than 20 years. And from the first time I saw him, he told me that he thinks in 5 years. And this has now happened 4 times. So, no, but I'll tell you what he meant, really. What he meant was that he did not see anything that is an obvious showstopper. So, yes, he hasn't succeeded yet, but but they make progress all the time. Only every time they hit upon another obstacle, and then they have to find ways around that, and so on. By the way, to make it clear, I'm talking about making life under conditions that are compatible with early Earth. That's what they're trying to do. Not just to make life however what, and so on. So that's what I'm talking about. I believe, again, it's very hard to make a prediction, but it is very possible that within a decade, they will have replication. This is now a big stumbling block, replication. Yeah. Yes?
If we do find the building blocks of life on Mars, will we be able to tell whether or not it came from an asteroid hitting Earth?
Yeah, very good question. Actually, you see, unless we find on Mars some life forms that appear to be from a completely different lineage than life on Earth, we will never be sure that they both came from the same source and and came from an asteroid from Earth. And the same is true, by the way, for the entire solar system. So unless we find, if we were to find life in the liquid methane lakes on Titan, that would be amazing. But otherwise, there will always be the possibility that, okay, life started in one of these and then it flew in the solar system.
Let's maybe take one more question and then other people can come and talk to this.
No, then I'll go sign books.
Yeah, one more.
Okay, one more question. Yes?
So let's say that you do find that there's water and chemicals that can sustain life, like for example under the surface of Mars. How are we going to be able to conclude that there actually is life there? Because like right now we're looking for signs of life, right? But how can we actually conclude and be sure that there actually is life?
I'm not sure I understand the question. I mean, if we will find some form of microbes, I mean, that do all these things that life does, you know, metabolism, this, replication, blah, 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 blah. We will call this life. There is no escape from that. Okay, thank you very much.
Thank you.